Good morning, everyone. Welcome to the Silver Jubilee of TNtalk. Let us start the program with the invocation of the melodious Tamil Thai Varthu.
கடலொடுத்த நிலமணந்த எழிலொழுகும் சீராரும் மதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் மதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம்பி எந்த செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Thank you, ACL team. TNtalk is a Government of Tamil Nadu initiative. On behalf of the Directorate of Public Libraries, we welcome you all to the wonderful session of TNtalk. Through a series of talks in different domains, TNtalks acts as a hub of information that transforms complex ideas into meaningful conversations, helping audience grasp new concepts and advancements. Every session is an opportunity to learn, engage, and expand horizons in diverse fields. It is not every day that we have the privilege of welcoming a scientist whose ideas have shaped the very fabric of modern physics, on whose contributions span decades, whose insights have unlocked mysteries, and whose passion for knowledge continues to ignite young minds. It is a moment of great privilege and joy to welcome Dr. Baskaran, a towering personality in theoretical physics and a guiding force in scientific discovery. Audience, please put your hands together to welcome him. Now, let us glance through a brief introduction of Dr. Baskaran. Dr. Baskaran is a distinguished Indian theoretical physicist, globally renowned for his pioneering contributions to condensed matter physics and strongly correlated materials. As a visionary thinker, he has left an indelible mark on modern physics with his groundbreaking research and influential discoveries. Dr. Baskaran has worked as a professor of physics at the Institute of Mathematical Sciences, Chennai. Not only does he excel as a distinguished professor at IIT Physics, but he excels as a distinguished professor at IITMadras. He amplifies his global impact as a distinguished research chair at the Canada's eminent Perimeter Institute. A proud alumnus of Tyagarajar College and the American College, Madurai, he earned his PhD from the Indian Institute of Science, Bangalore in 1975. His contributions and collaborations with Nobel laureate P.W. Anderson led to the development of the resonating valence bond theory, revolutionizing our understanding of high-temperature superconductors. Dr. Baskaran's journey is one of brilliance, innovation, and global recognition. He made history in 1983 as the first ever recipient of the ICTP Prize, a global acknowledgement of excellence in theoretical physics. His contributions earned him the Shanti Swarup Bhatnagar Prize in 1990, which is India's most prestigious scientific awards. The Indian Institute of Science, Bangalore, and Tyagarajar College awarded him with the Distinguished Alumni Award. In 2019, he was honored with the G.N. Ramachandra Shastra Award for his pioneering research. Now, with a big round of applause, let us welcome Dr. Baskaran to the stage to deliver the TNtalk.
நீங்கள் உட்காந்து பேசுகிறீங்க
காலர் மைக் இல்லையா? சரி, அடிக்கடி கை ஒன்றும். வணக்கம். First of all, I thank Dr. Vijayan and all friends from this library for hosting this talk. It's a very great opportunity for me to be with you, sharing with you about something about quantum physics in the next 1 hour or so. So I'm really, again, I want to say I'm honored to be here talking to you. So the title of my talk is, Thambi, the so how quantum physics has impacted society in the last 1 century, and so coming from Madurai, Tamil Nadu, quantum mechanics is out of syllabus for many of the students because it's supposed to be very boring and vague subject, lot of mathematics, so students avoid it. But somehow I got trapped in quantum mechanics. So I will share with you exciting things that has happened in the society in the last 1 century because of development in quantum mechanics. So that's my plan. And this is not often emphasized, so I want to emphasize how quantum physics as a subject, as an important development in the last 1 century, has impacted society. That's what I'm going to do in the next 40-15 minutes. I want to move it. இல்லை இங்கே பண்ணணுமா? சரி, நான் பண்ணேன். இல்லை இல்லை சரி. Okay. Now, I will just spend few minutes about myself because it's very important to acknowledge the love, sacrifice and guidance of family, friends and teachers. So about late 30s, a family of 5 migrated to Madurai, driven by famine from South Tamil Nadu. It was a very bad period apparently. 4 years they had nothing because Karisal Kadu, very dry area. So there was not much to eat. So people said, Vandi ketti Madurai poi Palakka povonu. It's about family of 5, 3 brothers, 1 sister and a mother. They migrated to Madurai, driven by famine. Hard work, mutual help, inter-religious tolerance. Poor but happy families bloom. So with 5 they multiplied in many number. My great father, beloved father and mother, my father had studied up to 2nd grade, my mother up to 8th grade. They worked hard and raised a family of 9 children. You can imagine, a poor but it was a happy family. My parents and our extended family taught us good values and give us full freedom. That is a very important thing. These days, people don't give freedom to children and also they don't teach them good values. So it's very important to teach good values and give them maximum freedom and love them. So Kamaraj's free education scheme and excellent school colleges nearby defined my career path. In those days, after 8th grade, you are put into some kind of apprentice in some shop or something. Then my parents told me because I am not failing in my exam so far, up to 8th grade I passed my exam, and Kamaraj's free education was available. அவன் சம்பாரிச்சு ஒன்று நம்ம பழைக்க வேண்டாம், படிக்க போட்டோம் அப்படின்னு என்னை அனுப்பிட்டாங்க. So that's how I went for education. And there was excellent schools, colleges nearby that defined my career. Let me just half a minute about my St. Mary's Elementary and High School, where I completed for 11 years. Tyagaraja Arts College, the American College, Madurai. None of them are education industries. They are all dedicated teachers. They want to teach people how to live and the quality of life and so on. So Tyagaraja Arts College is a fantastic college the management did not start the college to earn money. Similarly, American college. So then I know there are lots of, every step involves a beautiful story, so I will not go into that. I went to Indian Institute of Science. Incidentally, I have not heard about Indian Institute of Science before at all. Only during my second MSc, my professor Rees told me about the existence of that institute. When I was there, enjoying whatever came across me, I was doing science, without boundaries. So my professor was worried that I will never submit my thesis. Then my marriage was fixed. So they said that before I submit myself to my wonderful wife, I have to submit my thesis, which I did. That's how I got PhD. Then I worked in University of Madras, not far from here, in the Department of Theoretical Physics for 3 years or 4 years as a temporary reader. Then I went to International Center for Theoretical Physics, Trieste, Italy, and then to Princeton University, and I'm back at Madras University. Something in the bottom is missing. Thambi, கடைசி லைன் வந்து கட் ஆயிடுச்சு கொஞ்சம். Presently at, so பாருங்க, ஏன்னா கடைசி 2 லைன் கட் ஆயிருக்கு. இங்கே இருக்கா? Okay. So presently at I am at இதில் கூட வரல ஸ்லைடில். அப்படின்னா அந்த ட்ரான்ஸ்ஃபார்ம் ஒரிஜினல் இதில் இருந்தது மிஸ், அதாவது கொஞ்சம் இது பண்ணுங்க. பார்த்தீங்களா? ஸோ கரண்ட்லி ஐ எம் அட் த இன்ஸ்டியூட் ஆஃப் IITMadras as well as department Perimeter Institute of Theoretical Physics. I will tell stories about it later. So that's my briefly about myself. Okay. Next. So I acknowledge my contribution from my family, friends, and teachers. I had wonderful teachers. Without their guidance, I won't be here now. பரவாயில்ல, அடுத்த பேஜுக்கு போயிருங்க. Okay, good. Yeah, next. So you may have heard that last year was the 100th anniversary of the famous paper that S.N. Bose wrote and sent it to Einstein, and then that was the beginning of Bose-Einstein statistics. This was a breakthrough in quantum light and quantum matter. Thanks to efforts of Einstein, quantum theory got a boost. 1925, wave mechanics, matrix mechanics, etc. were born. So UN declared 2025 as the International Year of Quantum Science and Technology. So it's very appropriate that we are celebrating it. Next. So I have this slide which says that universe is quantum. Under Sarasaram, if you look at the universe, it's amazing that we finite beings, we live for a short time in the time scale of the universe. We occupy a small space, but you are able to comprehend the existence of the universe, things at a distance. And according to Einstein's theory, the universe began with a big bang. And that was the quantum fluctuations. There are beautiful quantum phenomena associated. I will not go into the details of that. So universe beginning is a quantum explosion, you can say. Then if you nebulae formation, galaxy formation, stars and so on. And our sun, if you look at it, which is giving us power and life, has arisen because of the sunlight that Earth constantly receives. It's a nuclear fission reactor, as you know. Energy is generated in the sun because 2 protons collide to produce an alpha particle, and there is a mass deficit which comes out as an energy. So special theory of relativity and also quantum physics works, and its sun is like Anu Ulai. It's like a reactor, fusion reactor. And we come to Earth, we have atmosphere, stones, mineral. If you take a piece of stone, kallu, mannu, if you want to understand it, the hardness of material, why it is hard, why you are not able to compress it, why its elastic properties so much, it needs chemical bonding and quantum mechanics. So quantum mechanics is everywhere. Similarly, if you take a piece of rust, thurun solramla, thuru eduthu, if you look at it carefully, it's supposed to be one of the most fascinating state of quantum matter called Mott insulator. There are electron spins which are giving rise to magnetism, and wonderful things are happening. So stone, mineral, magnets, metal, mountain, river, everywhere there is quantum physics, living systems, plants, animals, vision. I will discuss about ecosystem. Similarly, solid, liquids, and so on. Now if you go deep into the core of an atom, you have nucleons, then inside the nucleus, protons and neutrons. If you go inside the protons, there are supposed to be quarks. And if you go a little inside, there are gluons and so on. That's a standard model of elementary particles, which you understand. So there are theories of supersymmetry and so on, quantum gravity. So wonderfully, the universe is quantum, and quantum universe is also a wonderful thing. Next, please. Next. So science has performed miracles. One of the first miracles is the miracle of radio communication. The miracle of material science, transistor, it's the miracle of information technology. So these all you agree is happening because of radio communication, and then this change from valves to solid state transistors and information technologies. So science has opened us, given us new possibilities. A new discovery in solar energy can put the world in the right path to eliminate climate change catastrophe, because we are contributing to the greenhouse emission, green gas emission. So a new discovery of genetic engineering can make us angels. Quantum computers, room temperature, superconductivity, and so on could change. So new possibilities are opening up because of science. Next, please. What is different about human species? Fire, efficient communication, language, literature, art, religion, philosophy, mathematics, science, technology. We have a country, we have society, cooperation, collectiveness, weapons, we have fight also, despair, hope. And if you look at the history of the humanity, we have been fighting always, but as somebody said, the number of wars per person is much less now than it was before. Of course, any war is unfortunate, it's bad, it affects people, be it Israel war or be it Ukraine war. But they say because of science, there is a new hope. We will see that. An united world and new hopes. Next, please. So, since I am talking to young people, some of your students and so on, I want to emphasize the importance of mathematics. This is something, again, as I told at the beginning, when I studied in my schools and colleges, mathematics always got the last seat for many of us, because it's complicated. I remember asking my senior, trigonometry, triangle போட்டு hypotenuse, what is the use of it? Poor man, he could not answer me. Now I realize how important are Pythagoras theorem and triangles. So, according to Wigner, a Nobel laureate in physics, a famous Nobel laureate, he has written a beautiful article. I encourage people to look at this. If you do a Google search, you'll get it. Unusual effectiveness of mathematics in science and understanding natural languages. Because what has given power to modern science is mathematics. It's something extremely important. I will discuss that. Next, please. So science involves observations, experimentations, concept building, and mathematics. Held up, unfolding the secrets of. For example, if we take Newton's laws, it resulted from the observation by Galileo, Copernicus, and various people. So he said there are 3 laws. So the laws conceptualize what's going on. So you state the 3 laws. And if I tell my grandmother or uncle, they will appreciate Newton's first law and second law very easily. For every action, there will be an equal and opposite reaction. Everybody will continue to be in motion or a state of rest unless it is disturbed. So these are all laws that make common sense. So what? But the power of Newton is he handed it over to the mathematics, namely calculus. So that gave him the predictive power. For example, if you look at the Shoemaker-Levy comet collision, there was an amateur astronomer who was looking at the distant sky in the night instead of watching cell phone or instead of doing Ulium. He was watching the distant sky. He found a bright spot. He found out that it was a comet. Then he used his high school mathematics, Newton's laws, and calculated what will be the future trajectory given various planets in the neighborhood. He found after 4 days and so on, some particular time, it was going to collide with Jupiter. So he was shocked. So he informed the NASA scientists. They repeated the calculation, and he was quantitatively correct. So there was a collision. That's why it's called Shoemaker-Levy collision. So that's the power of mathematics. It can make quantitative. For example, if you send a rocket to moon, we'll have to do calculations. How much thrust, out of what angle it has to be. You simply use Newton's laws. Then you'll have to do calculations and make. It's not that in that sense, in that context, I want to tell about a great lady, forget her name. She was called a calculator. She, parent, not Shakuntala Devi. This is a lady from US. She was working for NASA. She was a black lady. She was a great calculator. She estimated the trajectory using Newton's laws and so on. When for the first moon landing and so on. There are beautiful stories about it. I'm terrible with the names, but it will come. So everything that if you are using cell phones, if you are using various things, everywhere there is mathematical calculation that goes in, using computers and analytical methods and so on. So mathematics is something very important. So that's one of the three pillars of, so observations and experiment is one pillar, and concept building and mathematics. So these are all, so mathematics is very important, please don't ignore it, particularly when it comes to quantum mechanics. We understand quantum mechanics only through the mathematics, because the other things are guessworks. I will come to that later. Next, please. So understanding some secrets of nature has transformed society, okay. So we have Newton's laws, as I was, calculus, Maxwell's equations, Darwin's hypothesis, special space-time relativity, and then quantum nature. Next. Yeah, I have already said that. Next. Yeah, next. Okay. Now let me, so how quantum mechanics has impacted society. Let me look at this history. Planck introduced the hypothesis of energy packets. I will discuss in some detail later. And then Einstein used it to explain photoelectric effect. Niels Bohr used that kind of idea to describe spectral lines that was seen experimentally. And S.N. Bose gave a beautiful derivation of Planck's distribution by identifying a key concept called indistinguishability of elementary particles. And then Bose-Einstein condensation came and so on. Then in this background, Louis de Broglie, he said that in quantum physics, something strange is going on. There is a particle which also has a wave character. So that's called wave-particle duality. So it's a hypothesis. He didn't know what to do beyond that. And Einstein saw wave-particle duality explicitly there in S.N. Bose's work. So then he was supposed to be examiner of de Broglie's thesis. He passed the thesis and so on. Then de Broglie is supposed to have given a talk somewhere in Zurich about wave-particle duality. Schrodinger was sitting in the audience. And there was this de Broglie, a famous physicist, sitting in the audience saying that, Mr. de Broglie, if there is a wave, there should be wave equation. What's a wave? What is the equation? Then there was an attentive audience, Schrodinger. He thought about it. He wrote down, he guessed what is the equation. That's called Schrodinger equation. That changed society. So then Schrodinger, Heisenberg, Pauli, all profound intuition, deep intuitions, guided by experiments and so on. Schwinger, Feynman, Dyson, Salam and so on. A collective effort unique in human history. Never in the human history people have worked together like this, because we have arts, for example, we have beautiful arts and literature in Tamil and various languages. It's a local effort, never a connection to what is going on in North America or South America or somewhere. Whereas here, you see people across the continent, mostly from European continent, America, and also from Asia, people work together, and it's a very collective effort. Now, this is also a forerunner to the collective international character of modern science. If you look at modern science, you look out to the library, look at the books. The books are from some author from Uzbekistan has written an article, somebody from Tanzania has written an article, somebody from New York has written an article. So it's a collective effort of understanding nature and making good progress. So, for example, if we take institutes, centers like International Center for Theoretical Physics, Institute for Advanced Study at Princeton, African Institute of Mathematical Sciences, Perimeter Institute, and many IIT, for example, IITM, Zanzibar, various things. Now, the collective effort is very visible. I will tell a little bit about LHC a little later. I do not know how many of you know about E8 group, supposed to be an exceptional group. It has thousands and thousands of irreducible representations mathematically. So to classify them, about hundreds of scientists across the world, mathematicians worked together and finally completed the classification. It was something like a human genome project where many people across the world cooperated and found out the first human gene sequence. So the human cooperation is fantastic. It's happening. You know this linear hadron collider, I will come to it, where you may have heard the discovery of God particle or Higgs particle. That was a fantastic phenomenon in which over years, about 2,000, 3,000 years, scientists have worked together from 70 different countries. Never in humanity people have worked together. And why am I talking about LHC is, we are all enjoying internet revolution and www. It started in LHC, CERN Geneva. Because they were generating a lot of data because of heavy electron and proton collisions. They were enormous data, they had to share it. So Bentley, one of the scientists there, he thought of the brilliant idea. Using the code www, he started sharing the thing, and which has changed the world now. So for you, www is very common now. So it's an offshoot of spin-off of quantum physics, where people try to understand how quantum physics gets modified, or how quantum physics manifests when you go to the level of proton, gluons, and so on. So it's one of the spin-off. Now at a personal level, when I was studying in Madurai American College, Richard Pires was a quantum scientist, a device physicist from Bell Labs. Apparently he came to American College for 1 year with his family, just for like a sabbatical. Then he fell in love with Madurai. He stayed there for 35 years. So he connected me to the rest of the world. And then I met Michael Berry at IISc, Area Society, and so on. So the quantum people whom I met have changed my life. So that just, so quantum mechanics science has united humanity and it's shaped various things. Next, please. Adutha. Okay, life is inseparable from light. So this is a picture I took a couple of years ago when we were traveling in California. We wanted to have some tea or something, so we went off the track and we went to the side road. We saw this, I took this beautiful picture. Look at the color, so many colors. So all this is due to the light that we are worrying about, the quanta of light. That's related to photosynthesis. Next. So light enlightens. Next. Okay, next. Okay. So it all started with Planck's observation and by others that if you look at a black body and try to measure the intensity of radiation as a function of wavelength of radiation that comes out, it defied classical mechanics and classical electromagnetic theory. What you see experimentally cannot be explained by classical theory. So what do you do at that situation? So this is where science and hypothesis and intuition comes. So Planck said, maybe I don't know what's going on, but however, if I make the following assumption that the energy is quantized, energy is appearing in the form of quanta, not continuous variable. So he says, if E is considered to be a continuous divisible quantity, this distribution is possible in infinitely many ways. We consider, however, this is the most essential point in the whole calculation, E to be composed of a well-defined number of equal parts and use there to the constant of nature, namely Planck's constant. So Planck, it was an ad hoc assumption. If I make this assumption, if I do some mathematics, I get a distribution, mathematical distribution, which is this, which agrees with what you see experiment. So it was a guesswork, but it's sharp mathematically, it's a very sharp quantity. And he had to introduce a constant called the Planck's constant, which is in this unit 6.58 times 10 raised to minus 16 electron volts second. The dimension of H cross is H is energy times second. So that's how you get this. So you notice there was no first principle derivation or anything. It was guesswork. So here is an experimental. In fact, many of these great discoveries come from experimental observation and deep contemplation, which results in some guesswork, and some of them survive like this. So because many people tried to guess this form, they did not find it suitable, could not describe it. Then Planck succeeded, and that was the beginning of quantum. So the whole point is energy appears in some quantized value. That's an important point that Planck made. Next, please. Now, a hallmark of the effectiveness of quantum mechanics from the beginning of the universe is this black body radiation called microwave background radiation seen from a distant sky. So suppose you have a telescope, powerful radio telescope, look at the distant sky, devoid of stars and so on. If you look at the distant sky, you will see a black body radiation around 3 Kelvin, which is very low temperature. So that's supposed to be the beginning of the universe, Big Bang. After some time there was a equilibration and so on. I will not go into the details. So that's evidence that quantum mechanics has been working for nearly 30 billion years. So nothing can be more pleasing than this beautiful distribution, which agrees with the Planck distribution that was suggested. Next, please. But again, science is fantastic. Planck never, even though Planck gave the idea of quantized energy, he didn't believe that they are some kind of particles. It was Einstein who said photons are some kind of particles, they are quanta particles. And he tried to explain photoelectric effect. Remember what is photoelectric effect? You take a metal like copper, shine radiation, nothing happens. Increase the frequency of the radiation. Beyond some, increase the intensity, nothing happens. But change the frequency. Beyond some frequency, electrons come out. And if you increase the frequency, nothing. Anyway, it's in aeroplane mode. So, now it's said that even though Planck is the father of quanta hypothesis, he never believed Einstein. So he says that Planck is supposed to have stated about Einstein that he may sometimes have missed the target of his speculations, as for example, in his hypothesis of light quanta, cannot really be held against him. But look at it. So Planck made the hypothesis of light quantized energy, and Einstein goes one step further, saying that no, light quanta is like a particle which can be absorbed by electrons and get excited and so on. Planck himself doesn't believe it. Finally, Einstein turns to be right. So this kind of dichotomy happens very often in quantum physics, because we are going into an unknown regime, unknown realm, where many things, surprising things can happen. So this is a beautiful debate between Einstein and Planck, who are the fathers of quanta. Next, please. Then there was this distribution, which hypothesis which Planck wrote down based on some guesswork and so on. According to Bose, who was at Calcutta at that time, and then he went to Dhaka, he was a teacher, very good teacher. He was not satisfied with the derivation of Bose distribution, Planck's law, distribution of photon gas coming from black body radiation. So he thought there should be a better way of doing it. So he looked at Einstein's work, and he found that there was some logical inconsistency even in Einstein's work, even though he said that Planck's derivation has two logical inconsistencies. And so what Bose did was, he re-derived Planck distribution using a hypothesis of indistinguishability of elementary quanta, and then he got a beautiful result, and then he sent it to Einstein. When he sent it to Einstein, he said, "Sir, I am your fan," basically, because both Saha and S. N. Bose, they had studied Einstein and Minkowski's papers on general theory of relativity, and had translated from German to English. So that was like a support for them. So he wrote to Einstein saying that, "Sir, I have already translated your book. I am an admirer of your work. So will you please look at my paper, please get it published." And you look at the stamp, two stamps. That stamp of Bose doesn't carry Bose-Einstein statistics. It carries gamma, which are general theory of relativity symbol. Okay. Next, please. So this is a paper that Einstein was impressed by. Next, please. Next. So a remarkably elegant derivation has been presented by Einstein. That's what Bose says. This author has recognized the logical deficiencies of all previous derivations attempted to derive the formula without reference to the classical theory. However, Einstein is also wrong. So Bose sends a paper criticizing Einstein's logical inconsistency. And Einstein accepts it beautifully, and then goes beyond that, and then applies it to a material particle with a finite mass and gets a Bose-Einstein condensation. So that's the level of Einstein-Bose relation, which is again an important connection between humanity at different places in space, different culture. They work together and they open a new door to the development in society. Next, please. Okay, this is de Broglie. His intuition is that if there are waves, the wave should have wavelength, then like if you take a vibrating string held at the two ends fixed at, then they are various modes of vibration. So he thought of similar modes of vibration, and the wavelength, he said, should be connected to momentum. Just a hypothesis. He used the hypothesis of Planck's constant, because Planck's constant had the right dimension, so that if you divide it by p, you get the wavelength lambda. So that was an intuitive leap, but sharp mathematical observation. And de Broglie's thesis was not impressed, it did not impress Einstein. Once Einstein saw the paper of Bose, he understood the deep meaning of Bose's work contribution, immediately approved de Broglie's thesis. Next. Next, please. Then Schrodinger, he wrote down the wave. Again, it's a guesswork. What do? You have energy expression, which is p squared by 2m plus potential energy. And then you replace classical momentum variable by an operator. That was an ad hoc statement, but including Planck's constant and so on. That explained the spectra of hydrogen atom and so on. The Niels Bohr, I missed the Niels Bohr, I should have mentioned it too. But anyway, next please. So Schrodinger has a book called What is Life? I encourage people to read it, because he was worried about biology, phenomena of life, and how life emerges, plants emerge and so on. So he said that quantum mechanics plays some important role, and in the process, it's a fantastic thing. If you take a book of genetics, modern book on genetics, typically the first full page is about Schrodinger's contribution. Schrodinger is not a biologist. What he said was, if genetic information has to be transferred from one person to another person, the hereditary information, for biological functioning, because chemical bonds are involved, it has to be in the form of a one-dimensional sequence. So he called it a subperiodic crystal. So it was, even before Mendel and so on, they said there will be a genetic information. But in what way the genetic information is coded, nobody had an idea. Schrodinger, using his quantum insights, chemical bonding insights and so on, he hypothesized that it has to be a one-dimensional sequence. That was the beginning of what we call as DNA. So any genetics book will acknowledge Schrodinger's great contribution. Next, please. Okay. Then the rest is history. Many people took up on this Bose and Einstein's work, de Broglie and Schrodinger, and came Pauli. He founded the exclusion principle, and Dirac. So that was, the rest is history. I'm just telling you history. Now I will go into how it impacts society. Next, please. Let me first tell about a local phenomena, how it has impacted science at Chennai. Sommerfeld, a great scientist, he had produced at least 3 Nobel Prize winners as students. He was a remarkable scientist. He was invited by Sir C.V. Raman to Calcutta. In those days, the ships land at Chennai. So from Chennai, you take a train and you go to Calcutta. So young Chandrasekhar was a student at Presidency College in Chennai, BSc student, very curious and very inquisitive student. He used to do more than his classwork. So at Sommerfeld and Presidency College, he gave a lecture on new quantum theory of metals. That's when quantum mechanics was being developed and being applied to other situations. Like the famous Linus Pauling applied it to chemical bonding. Then if you take a metal like copper or aluminum or lead, they exhibit so-called Pauli paramagnetism, and then also linear specific heat and various things. So they were all experimental facts which could be easily measured experimentally, but there was no explanation. Then what Sommerfeld did was, he idealized the behavior of electrons in a solid as being plane waves. Then he used Pauli principle. He said in a plane wave state, not 2 electrons more than 2 electrons cannot be there. If there is an upspin electron, then there has to be a downspin electron. Then it automatically creates what is called a Fermi sea. So he gave a beautiful lecture about it. Young Chandrasekhar, very inquisitively, he listened to it. So he was fascinated by star phenomena and possible collapse of stars and so on. Because if you take a star, big enough star like a sun, there is always a gravitational pull which is holding the star. And there are other forces which is trying to explode it. So at a particular stage in the evolution of stars, 2 things are main. One is a gravitational pull, another is the so-called Pauli pressure, that is Pauli exclusion principle, which says that 2 particles cannot be in the same state. If you look at equation of state, it occurs as a repulsion. So Chandrasekhar basically applied it to relativistic matter and then got his name. Chandrasekhar's mass limit, black holes, beginning of modern astrophysics, astronomy, new telescopes, and so on. It's amazing how a single lecture of Pauli Sommerfeld visiting Chennai made a big difference. So I request students to please attend lectures, It's very important to listen to these kind of people. And why I'm saying this is, we're all enjoying digital camera because many of us have digital camera. We take many snapshots. If you look at the history of digital camera, at some point we were using films. Then came what is called charge-coupled devices, and very sensitive solid-state devices were developed to advance radio astronomy and advance optical astronomy. So an offshoot of was that the Sony camera. Apparently those were used by some of these Japanese companies. Now the world of photography is completely different. So digital camera is one of the offshoot of quantum physics, one of the many offshoots. Next, please. Now, where the telescope has gone is amazing. Now the telescope and precision this is supposed to be a picture of, if you look at the sun, there is a lot of flares going on. We see it at some level in photographs. Now the telescope has so much advanced thanks to quantum physics and the quantum devices that this is a picture of, there's a telescope called Unification telescope. They have looked at a local boiling sun, turbulent sun, and the scale is like 10-15 kilometers is a resolution. So when I showed it to one of my child, he said, "Tata, idu kadala mittai mari irukku appadinu." So it looks like very sweet of him to say that. So I told it to my friend. This lecture I heard from K.R. Srinivasan, the distinguished stellar scientist who was at New York. So I knew him from my PhD days. So I told him the story of the kadala mittai. So he was very excited. He said, "Please send that boy when he grows into a big boy for me as a PhD student." So, but the boy may do something else. Anyway, so that's the power of telescopes. Again, the roots can be connected to quantum physics. Next, please. Next. Okay. Now, before I go to the application, see, Madras in some sense is a great place for quantum physics. Several good quantum mechanics books are available. For example, outstanding quantum mechanics courses in NPTEL. If you take national NPTEL, if you look at the number of courses offered by all the 23 IITs and IIScs together, about 800 courses are available from April to May. About 10-20 of them are quantum mechanics. Outstanding courses, quantum computing and so on. And also, we have a famous course of lectures on quantum mechanics by Professor V. Balakrishna of IITMadras, my colleague, who is 80 plus but still very active, dynamic guy. He's a great teacher. I encourage you to learn quantum mechanics from him. In fact, somebody said that, in Tamil Nadu, we know about Kolaveri part 3. It's the greatest hit. அதுக்கு அடுத்தது தான் ஹிட் அப்படின்றாங்க. Balakrishna, V. Balakrishna, the hit he has given so many, people are inspired by all over the world. அதே மாதிரி R. Shankar, he was an IITMadras student, did electrical engineering, then he decided to switch to physics. He went to Berkeley, did a PhD in particle physics. Now he's a big professor at Yale. He's also a great quantum mechanic. And then Professor Matthews, P.M. Matthews, Department of Theoretical Physics, he and Venkatesan has a beautiful book on quantum mechanics. So there are many, and my institute at Chennai, Department of Theoretical Physics, and IITMadras, they are all full of quantum mechanics. If you have any problem in quantum mechanics, please go to them. So there are also beautiful courses for high school students called Qubit by Qubit. I encourage you to look at it. Anybody can register for it. There are scholarships available freely. So they teach you very elementary things. Just if you know 2 by 2 matrices, how to manipulate, you can go a long way.
Sir?
Yes?
With due respect, if you don't mind me interrupting, can I ask a question?
Please, where are you?
Sir, here.
Please.
Myself, Priya, I have a bit of curious question that I have to ask you is that what encouraged you to opt for this particular point of science? Because something would have been in you that would have led you to choose this science. So,
It's a very good question. I had okay, let me tell you a small story, how I became a physicist first. I completed my pre-university. I got second class. because it was a transition from Tamil medium to English medium. So I didn't know what to do. Then my parents said, ஒரு காலேஜ் இருக்கிற படிட்டா ஏதாவது படிக்கிறான். So I studied pre-university and then got second class. I wanted to become an engineer because I was good at making things with hands. So I thought I will become an architectural engineer. Then no engineering college will give me admission because I got only second class. So I didn't know what to do. So then Tyagarajar College was there. My parents said, "Anga poi cherra appadina." So I didn't know which group to join. So I had left the group empty and walked to the principal's office. My friend Krishnan was coming out. Hey Krishna, enna group la eduthirukanu ketten. Physics appadina, physics in potten. That's how I became a physicist. So series of accidents like this. So then when I was my first year, my professor was unhappy that I got very low marks. I was happy that I got 70. எனக்கு பெருசாக இருந்தது. அவர் என்னடா 90 வந்துட்டு எதிர்பார்த்தேன் 70 தான் வாங்கியிருக்குன்னு என்னை வஞ்சார். So then I got very excited. Maybe even I can get marks. I started studying. So the மாதிரி quantum was, I'm very happy I'm remembering this. See, மதுரையில் வந்து when I was studying there used to be some libraries. டேவிட் ஆக்கிஸ்கிட்ட ஒரு பெரிய லைப்ரரி, இந்த மாதிரி முக்கியமான லைப்ரரி இருந்தது. அங்கே போனேன். I got a book on quantum mechanics by Dirac. So I took it for whatever it's worth. I read it, but I didn't understand anything, but something must have gone in. I remember during my BSc or MSc days. Similarly, there was a beautiful library near my house, so I used to go and borrow books. So libraries are very, not now, but those days it was very useful. Anyway, that's how my opting quantum physics was, I do not know, I am not responsible for what I am doing. That's somebody else guided me. Yeah.
There are different branches of physics. Where did you select?
Okay, good. So, sorry, again many stories. So Professor Rees, my teacher, said that, Baskaran, you have some momentum, so you should go to Indian Institute of Science. I told him, என்ன சார் அது அப்படின்னா என்னன்னு கேட்டேன். அது பெங்களூரில் ஒரு ரிசர்ச் இன்ஸ்டியூட் பண்ணி எனக்கு சொன்னார். Then I applied there. I did not get admission in physics because I got second class in my pre-university. Because they have a way of screening, they didn't think. But fortunately, I got admission in applied maths department because I was fascinated by mathematics. Then I was there. Then when I was in the third month, Professor Narendra Kumar, a great quantum physicist, joined IISc as a young assistant professor. He gave an inspiring course on quantum matter. That's how I shifted to that as a teacher again. I was not prepared or anything for. So then I got shifted. Then I worked hard and failed and so on. And then, anyway.
Dear audience, you can ask the questions at the end of the talk.
Yeah, okay. Anyway, I had an opportunity to walk. Thank you. So, next please. So how are we doing with respect to time?
You can carry on, sir, with the talk.
அப்படி சொல்லலாம், போயிட்டே இருப்பேன் நைட் வரைக்கும். So what is special about quantum physics is something uncertainty. It's very amazing how things being uncertain leads to new physics and new revolutionary developments. In classical mechanics, everything is precise. In principle, you can tell the trajectory of a part. Suppose I throw a stone, I know which path it will follow and when it will fall down, given the background G and so on, gravitational pull. Similarly, I can calculate in principle you can do a calculation. But quantum physics, even in principle you cannot. There is an intrinsic uncertainty. So that's the difference of quantum physics from classical mechanics, particles, fields, Newton's laws of motion. So, but, next please, yeah. Degree of uncertainty is quantified by Planck's constant. There is something called a Planck's constant, which Planck introduced without knowing that he is going to introduce uncertainty principle eventually. It puts a lower limit on uncertainty, something called Heisenberg uncertainty, which says that suppose I have a particle moving in a line, then according to quantum physics, if you know where the particle is sharply, then the momentum will be uncertain because delta x, the uncertainty in position, times delta p, the uncertainty in momentum, has to be always greater than h cross by 2. Minimum value is h cross h by 4 pi. So you cannot go below some minimum value. The uncertainty can be much larger. So orbital, this is a fascinating phenomena of quantum physics, where there is intrinsic uncertainty, which nature seems to follow. It was guesswork of Planck and others. We landed on understanding. I will tell about what is Feynman's statement about this uncertainty and so on. Similarly, every observable, like angular momentum, of electron is because if we have an electron orbiting around the nucleus, so the angular momentum, because of uncertainty, has sharp values called quantized angular momentum, angular values. Similarly, if you think about an electron as a spinning, like a spinning top, it's called spin angular momentum. That's also because of uncertainty, has sharp values, namely half or minus half. So it has profound consequences. Again, due to one constant, see, this always mystifies me, how Planck introduced a constant to explain experimental results. And the ramification was profound everywhere, Dirac's theory and so on. Okay, next. Now, one of the recent papers in Nature, so one of the consequences of this uncertainty is something called cat state. In fact, this is called Schrodinger's cat, because Schrodinger did a thought experiment. He said that in principle, I can create a state in which a cat is alive and also dead. So this is counterintuitive, like, but in quantum mechanics it's possible. There are many examples. For example, I can say that I am here inside this room and also I am outside. So classically it's not possible, but quantum physics allows that possibility. But of course, to prepare such a state with a macroscopic object is extremely difficult, it's impossible. Whereas with the electron you can do it, because the electron can be inside and on one side of an atom or another side of the atom, it can quantum tunnel and so on. So many counterintuitive things happens with quantum physics. That's a remarkable thing about quantum mechanics. So recently in this paper, they have created a state in which the spin is up plus down. So with some probability you will find it up, with some probability you will find all of them down. So to go continuously from one to another is a very long path, but however you can prepare a state which is called a Schrodinger cat state. Just next please. Sorry, many of the things that I am telling you may look very strange to you, but I am rushing. So laws of physics are different at the atomic scale. They are counterintuitive. Newton's laws give up and laws of quantum mechanics emerge. Particles behave when de Broglie. So the box is supposed to be H, Planck's constant. So there is a measure of, suppose how quantum mechanical I am, then what I will do, then I will have to calculate my de Broglie wavelength, which is take Planck constant, divide by mass, about 60 kilos or 70 kilos, and my velocity, then you will find it's very, very small distance, much less than 1 angstrom atomic dimension. So macroscopic objects do have de Broglie wavelength. The wavelength is extremely small. But when you come to electron, the wavelengths are, they live coherently in some atomic dimension, so they were comparable to the electron atomic dimension. So quantum physics is very important. So that's why there is a transition from classical to quantum physics continuously. So in principle, using quantum physics, you can derive all the Newton's laws. That's called law of correspondence. In principle, you can derive all the classical laws using the limit Planck's constant go to 0. So for macroscopic object like you and me, quantum physics is not important. But however, when you come to the level of electron and the processes that go on in our body, quantum physics is extremely important. Similarly, photosynthesis and so on. Okay. So what is important? Most common quantum phenomena defies common sense and our classical intuition. This is where students get very unrest. Let me say. Next, please. Next. Next. Okay. So Richard Feynman is, is a great physicist, one of our greatest in the last century. I had the honor of meeting him once. He was at Princeton and he gave a colloquium at Bell Labs. So Phil Anderson drove me there. So I listened to him. He was a master speaker, fantastic. He was talking about 1984 November quantum computer. Imagine 40 years ago. He was talking about quantum computer. How do you, suppose you have qubits, how do you connect them by wires and so on. So he was far ahead of his time. So according to Feynman, you are not alone. I think I can safely say that nobody understands quantum mechanics. So do not take the lecture too seriously, feeling that you really have to understand in terms of some model which I am going to describe. Just relax and enjoy it. So if it's Bohr atom model, just enjoy it. Don't worry how it came. Just understand the model. I'm going to tell you what nature behaves like. We will simply admit that maybe she does behave like this. You will find her a delightful and entrancing thing. So we see things at a macroscopic. So we have an intuition about our world. But when you go to, we have to be humble when you go to atomic level, things are different. So enjoy that. So don't worry about why it is so. You can later worry about it. But just, in fact, in some place, Feynman says, shut up and calculate. In quantum mechanics, don't ask questions, shut up and calculate. Because if you can calculate, if you can predict, you can get a Nobel Prize. So do not keep saying to yourself, if you can possibly avoid it, how can it be like that? It's like when I say quantum mechanics, uncertainty and so on, Schrodinger cat state, you start saying, how can it be like that? Because you will get down to the drain into a blind alley from which nobody has escaped. Nobody knows how it can be like that. So these are honest statement from Feynman about quantum physics. So let's not be worried if we don't understand quantum physics. Enjoy it. It's like music, you know. You enjoy music, right? You can't create music, but when you listen to music, you enjoy it. That's the way it should be. Yeah. Next. See, S.R.S. Varadan, again, an alumnus of Presidency College. He's a famous mathematician. He visits Matscience sometimes. So he got the famous Abel Prize. So he says over the years, the mathematics of quantum science has become more abstract and consequently simpler. That's what a mathematician says. The more abstract is, for them it is simpler. For those of you who love mathematics, modern quantum mechanics, many-body theory, field theory to support a wonderful world of modern mathematics. Further, modern physics has helped emergence of some new mathematics. So quantum physics can be an entry point into the rich world of mathematics. So quantum physics has done many things, including entry to the new world of mathematics. Next, please. Okay. Next, and then I'll come back to it. Next. One of the effects of quantum physics is the following. There was Abdus Salam, famous for his standard model, where he tried to understand what is going on at the level of quantum field theories, at the level of protons and neutrons and grand unification, standard model and so on. So Salam was a kind man. He was a humanitarian. He was seeing the suffering of third world countries, and he wanted that science should be help humanity development. So he was lamenting to one of his friends, Paulo Budinic, who is the first person in this. He said, Paulo, I want to do something to my third world countries because they are ignoring science. So I want to do something. Budinic said that, don't worry, I am from Trieste, the city which is in the northern part of Italy. The mayor is a good friend of mine. I will get a large piece of land for you. Do whatever you like. So that's how International Center for Theoretical Physics was started. So it has touched the lives of many scientists from the then developing, and now China will not call it as a developing countries, or India will not, because we are developed countries, we are developing. China is definitely far advanced. But 50 years ago, it was not so. So the theoretical physics development in China and in general science development owe a lot to the effort of Abdus Salam. So let me narrate one incident. You see the Dirac, the second person from the right, tall gentleman, his wife. So I landed in ICTP not long back, 1976, January, about 50 years ago. And it was a 3-month school on interaction of radiation with matter. I should acknowledge, my travel fellowship was arranged by my good friend Subaya Arunachalam, a scientiometrist and a librarian and so on. So he arranged me, otherwise I would not have gone. That's why it's good to have friends like Arunachalam. You get, support. So I ran there, and Salam welcomes us by saying that ICTP is due to put you together the best scientists from the world. Rest is for your effort. So the school is going on. I'm enjoying the school. There is a top floor where there are big rooms. So maybe our students are sitting there. Once after I was observing that there was an elderly gentleman sitting next to my office. I asked somebody curiously, who is that? He said, don't you know, he's Paul Dirac. Then I remembered Salam's statement, the rest is your effort. So he has put us with the best mind from the world. Paul Dirac was visiting ICTP for a week, so I had the honor and great thing of seeing him. So this is the effect of, a quantum physicist who wanted to help third world, and now the effect of Salam's effort is fantastic. There are at least 10 ICTPs all over the world, branches of ICTP. Similarly, there are genetics institute and various international cooperation started from a quantum physicist. Next, please. Please go back. Sorry. Go back. Back. Yeah. Again, I will see. You see this called elementary particles that appear in standard model. For example, if you take a proton, supposed to be made up of 3 quarks, which form a color singlet, then there are gluons which are binding them and so on. So this is a simple table which summarizes the standard model. What you see is something called Higgs boson and Anderson-Higgs mechanism. I will come to it. Yeah, Bose condensation of Cooper pairs. So I'm showing this because in physics, similarities are amazing help. Similar phenomenon that happens in a dirty piece of material will have ramification in understanding elementary particle physics. So what is seen in turbulence in fluid, you can try to understand the red spot in Jupiter. So similarities are very common thanks to mathematics, because the mathematics of phenomena happening at different situations, different scales, when they are identical, there is an unification. Next, please. I will. Next. Yeah. Okay, next. Okay. And also one of the fascinating things about quantum physics is when you put things together, many surprises happen. That's called, Aristotle is supposed to have said that the whole is more than the sum of its parts. Science, literature, art, life exemplifies this. Contents and components differ from situation to situation, and the nature of emergence continues to surprise us. That's what makes emergence exciting. So the application of the way society has benefited from quantum physics can be thought in this emergence context. I will not elaborate it, but just to give you a little example. Next, please. So you say that complexity number more than the sum of a plus a is greater than 2a. Put two things together, it's greater than 2a. Next. So you see two concentric circles, right? Beautiful circle. Bring them together. Some people say it looks like butterfly, or some people say it looks like insect moving in the water. Next. Now it looks like two eyes, right? Or some butterfly. Next. It looks like a cat. So if you looked at the circles separately, you would not have guessed that this will emerge. So this is what happens in emergence. Emergence, when you put things different things together, many surprising, that's what this physics is all about. So this is called the Mayer pattern, which is very important in the recent context in quantum materials like graphene, Mayer pattern, graphene, what is it? Twisted bilayer graphene and so on. Next, please. Okay. Now, let me again, how it has helped society, it is a seed of this. Emergence and hierarchical structure is well known in biology, because if you give me an atom or a molecule, can you say life will emerge? There are a series of phenomena, amino acid formation, DNA formation, nucleic acids, putting together protein, various things happen. Even we don't understand how to create a bacteria. We don't understand the physics. There are so many Nobel Prizes even to be given to understand a bacteria. So leave alone a big life like human beings or elephant or whale. So emergence and hierarchical structure is unique. And there was a debate between Ernst Mayr, a distinguished evolutionary biologist, and Niels Bohr. Niels Bohr is our Bohr. So he tells the following. It's a way of looking at physics. So he says, okay, take hydrogen atom, I understand it. So Niels Bohr hydrogen atom models. Put two hydrogen atoms together, it forms a molecule. Okay. Bring an oxygen, then it forms a water molecule. Okay. Then you put more water molecule, there is water cluster. Then you have hydrogen bonds. Then you have ice, which has quantum mechanical property. Then you pour a piece of water, pour a bucket of water, it's turbulent. So, if by knowing the property of hydrogen or hydrogen molecule or water molecule, can I predict the existence of turbulence? No, because at every level, new things, hierarchy of level, new things happen sequentially. So it's very important to recognize that. So that's what happens in quantum physics. So I will illustrate again with some examples. Next, please. Next. Yeah. This is very nicely written. There is an article by Phil Anderson called More is Different. I encourage you to look at it. Let me, because of lack of time, let me proceed further. Next. 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 Yeah. See, we start with the hydrogen atom. You have molecules, you have protein, DNA, and many things happen. Next. 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 Okay. Again, a consequence of, see, while quantum mechanics was being developed, Dirac came. He was very unhappy that Schrödinger's equation did not incorporate special theory of relativity. Nowhere velocity of light appears. So he says, special theory of relativity is very important. So how do I do it? Then he does a mathematical trick. He says, I'll have to take an operator and take a square root, whatever it may mean at that time. So he ends up with what's called Dirac equation. So it is a pure mathematical curiosity, pure intention to incorporate special theory of relativity into the mathematics of quantum mechanics. So he ends up what is called relativist quantum mechanics. And then what he finds is, when he looks at the mathematics consequence of the solution of this relativistic Dirac equation, what he finds is there are negative energy states which are filled and then empty states above a mass gap. So Dirac predicted, purely using sharp mathematics, existence of positron, an antiparticle of electron. So electron's existence was known thanks to Rutherford and many others. So it has a charge E minus charge E. And then positron was a prediction of Dirac's theory. When Dirac wanted to say that I am unhappy with Schrodinger equation because it doesn't satisfy special theory of relativity. So he built a relativistic quantum mechanics theory which predicted the existence of positron. It's a missing electron in a filled negative energy states of filled Dirac sea. So this is Dirac sea. Now, how do you know? I mean, this has implication in our modern life in the following sense. So next please. I said analogies are extremely powerful. So Dirac gave just out of curiosity, in order to incorporate special theory of relativity, he landed up in Dirac equation, electron spin and so on, various things, including a mass gap and a positron and so on. So then in parallel, our condensed matter physics friends like Wilson, they were studying behavior of electron in a semiconductor. A semiconductor electrons are moving in a periodic potential well. So they fall what called block states. And you know that if you take a piece of stone, it's insulator. You take a piece of copper, it's conducting. So what's the difference? Then quantum mechanics explained that in an insulator you have filled bands and an energy gap and then excited empty states. In a metal you have unfilled bands, so there is conducting. So roughly we understand. So now what Wilson and others did was, so if you have a valence band which is filled and you have a band gap, it's an insulator. Now this is where John Bodin, Bratton and Shockley come. They knew quantum mechanics very well, particularly Bodin, and they wanted to exploit it. So that made a big difference. So they wanted to use the idea of Dirac. They said that if we take a semiconductor valence band and then remove an electron by, suppose I take silicon, right? You know the nature of bonding in silicon. Replace one of the silicon atom by phosphorus. So phosphorus is next to silicon in the periodic table. It has one extra electron. So what will happen is the extra electron will get roughly bound, or it will form an impurity state. So that state will lie in the gap. So it will be called a N-type state. Similarly, if we, instead of phosphorus, if we put what is to the left of silicon in the periodic table? Some I think aluminum or something. Sorry? Aluminum, yeah. If you put aluminum, then it has one missing electron, so it will create a hole. So the Dirac's idea of electron and antiparticle comes in a very beautiful way through analogy. So there is nothing like a positron here, but a missing state will act like a positive charge. So that's a filled bands in semiconductor band gap, hole a missing electron within. So once it was recognized by Bodin and a company that if you put a P-type and N-type semiconductors together, some band realignment will take place and you have this fantastic rectifier action. That's the beginning of semiconductor revolution. Look at how quantum physics has impacted Planck's constant, photoelectric effect, Bohr's atom model, Bose-Einstein hypothesis, condensation, de Broglie hypothesis, and then Dirac's theory of mass gap, positron. It gets applied to a very completely different situation, namely a simple solid like a semiconductor, silicon or germanium. So doping can be at the mathematical level there is grand unification. If you look at the mathematics of the band gap and so on, it looks like relativistic theory with appropriate Fermi velocity replacing the velocity of light and so on. So these were analogies that are extremely useful in physics. So the analogy of what Dirac discovered was used in the kind of solid state, and you know the world has become different now. Next please. So from vacuum tube we have gone to semiconductor, field effect, magnetic, and wonderful things. Next please. Next. Okay. So I had the honor of meeting John Bodin, 1976. So I was just submitted my thesis, and I was a postdoctoral fellow at IISc Bangalore. So John Bardeen visited IISc. So professor spoke to him. John Bardeen is a man of few words. பேசவே மாட்டார், அமைதியாக கட்டுக்கிட்டே இருப்பார், தலையாட்டிக்கிட்டே இருப்பார். After some time, professors got very bored. They didn't know how to handle him. So they found me convenient and they handed me John Bardeen to me. Because my professors were away, I was only senior most fellow theoretical physicist. So இவரோட பேசலாம் அப்படின்ட்டு. Then John Bardeen opened his mouth. So we had 2 hours of intense discussion about physics I was doing at that time. It was very encouraging when I told him my old ideas and so on. So professors வெளியே வந்து என்னடா நீ என்னடா ஒன்ட்ட மட்டும் அவர்கிட்ட பேசுகிற, என்கிட்ட பேச மாட்டேங்கிறார் அப்படின்னாங்க. Anyway, that was John Bardeen. Then in 1987, I go to Urbana-Champaign to talk about the theory of superconductivity that Phil Anderson and we developed. So I gave a colloquium. John Bardeen was in the audience. So when the conference is over, people come and congratulate me. I thought I gave a good talk. இல்லை நீ சாதாரண டாக் ஒன்றும் பெருசாக இல்லை. Why are you congratulating me? Because you made John Bardeen ask 3 questions. He has never asked questions in the colloquium. So that's my interaction with John Bardeen, great man. I also knew his 2 sons, Bill Bardeen and another Bardeen. One is a cosmologist, one is a high energy physicist. Anyway, these are all the people who have changed the world now using quantum mechanics, using analogy to Dirac equation and the ideas. So the world has to become different, miniaturization and so on. Next. Sorry, let me, I think I should. Time என்ன? 12:30. So when did I start? 1 மணி நேரத்துக்கு மேலே போயிடுச்சு. ஓகே, அப்போ then it's time to stop. Okay. So let me very quickly. So like solar power is the most promising energy. Next, please. Next. You all, when you go out, you see beautiful flowers, green leaves, photosynthesis is going on. And fantastically, photosynthesis is a beautiful quantum phenomena, quantum coherent phenomena happening at room temperature. It's being discovered. So biology can beat room temperature, beat the conditions for coldness and special conditions. Biology can create special conditions even at warm temperature and use quantum coherence. So that's what photosynthesis is. So there's a new field opening up for the future of energy and so on. So very soon solar energy panel will be replaced by biological things using photosynthesis. I have no time to explain it. Next, please. Next. So Feynman said that there is, just go back. I encourage students, there is plenty of room at the bottom. So Feynman is supposed to have said that when you go to the level of atoms and molecules, many counterintuitive things happen. So you can use it to their advantage. That's the beginning of quantum computers. The way we use electricity. Next, please. So use quantum. Next. Please keep going. Next. Okay. Next. So it was discovered by Cameron-Wonnes that if you take mercury and cool it down, it loses all its resistance, called superconductivity. It's a fantastic quantum phenomena at a macroscopic scale. It's called a macroscopic quantum phenomena. Next. It was also found that there is a Meissner effect. That is, if you bring a bar magnet, the magnetic flux are expelled by the superconductor, so it can work against gravitational force, it can float. Next. So that means you can use it for frictionless travel. That's magnetic levitated train. Next. My friend Kitazawa, he is no more. He gave a talk, I gave a conference committee talk, I called it as Kitazawa's dream. His dream is, next, when you connect the world by superconducting grid, using cuprate superconductor or others with solar panels and windmills, and he did an estimate, he did a serious calculation, found that it will be cheaper than whatever money we are spending, even though if you put liquid nitrogen all along. But provided countries cooperate, that's where the problem lies. Next, please. So next. So he has many ideas. So the world will become very different. Next. For example, he says magnetically levitated trains, this path, it will decrease carbon footprint enormously and the world will become, again, provided countries cooperate. And I told him I'm very happy because I found that the train, this route passes through Madurai. not Chennai. So I was very happy. Anyway, next. So there is something called quantum entanglement, again very counterintuitive phenomena which can be made use of for quantum physics. Next, 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 next. Okay, just go back. So before I complete, if you take a classical computer, what you do is you have an algorithm. You start from the initial condition. If there is a path, calculation path, you get a final result. Next, please. Quantum physics is amazing. It does, like Ashtavadana Madhuri, simultaneously many things at the same time. So you want to go from initial state to final state, and then it explores simultaneously many paths. That's why it's super efficient. So like you have a dissipation less 50 qubit computer with long lifetime can overwhelm all the computers put together in Tamil Nadu, for example. So there's a great promise because of this vagueness or uncertainty, which is part of quantum mechanics, that also gives you a power. Next, please. Anyway, next. Okay, this is my last. So we are all using ChatGPT and quantum and so on, right? If you look at the root of this modern article, there is a beautiful connection to quantum physics. That's what I wanted to tell about before I finish. So it was observed by people that quantized spin of electrons forms a ferromagnetic or antiferromagnetic coupling. So there are situations called spin glass models where spins don't know what to do because they're competing. Suppose I have 3 neighbors. My first neighbor says you stand up. This fellow says stand down. This fellow says, so I am getting competing information from neighbors, so I'm frustrated. So I don't know what to do. That kind of things happen. And it was written as a time model by Edwards and Anderson. First is Anderson, that's Edwards. And John Hopfield, a friend of theoretical physicist, a good friend of Phil Anderson, applied it to how brains function, the elementary model of neural network. That it's the beginning of machine learning, Boltzmann machine deep learning, and John got Nobel Prize just this year, as you may remember. So again, a personal anecdote. In '84, John Hopfield gave a beautiful talk on neural network theory because I was familiar with spin glass. I got very fascinated by it. Next 2 years, I spent my time learning neural network and neurobiology. Then after that, I came back to physics. So I wish to go back to it now, but there is no time. Next, please. So quantum science continues to contribute to the field of medicine and health science, imaging, arts of things. Next. Yeah, next. Please keep going. I'll come to the end. Please go back. So science and technology has made humanity big. Never in the history of Earth there were so many human beings, 120 crore of Indians, big family of several hundreds of crores of women. Hope that science and technology will make this big family into a happy family. Thank you very much. Sorry for taking more than 1 hour.
Professor Baskaran traced the impact of quantum physics. He acknowledged the contributions of Newton, Planck, Einstein, Bose, de Broglie, Schrödinger, Feynman, and all others who had contributed to quantum mechanics. He emphasized on the importance of mathematics in science and usefulness of collaboration in research. Thank you for the wonderful presentation, sir. Now it is time for question and answer session. Maybe we can limit the question and answer session to 4 questions. So audience, if you have a question, just
Hello.
raise your hand.
Yep, I'm here. Sir, it's a wonderful session. I got a lot of insights. So my question is very simple. Actually, I don't have a physics major, so I'm a psychology major, but I'm so interested to about the consciousness. So some theories in quantum mechanics plays a crucial role on consciousness. For example, Roger Penrose. Yeah.
So this is a very important question. See, self-awareness and consciousness, we can't even define what it is. So there are many people like, Gurujis and so on, they say quantum mechanics can explain consciousness. I don't believe that.
Yep.
Because, see, John Hopfield, the Nobel laureate, he's my old friend. So he gave a talk at Matscience online 2 years ago. So I asked him, John, what's your feeling of consciousness? What is your theory? He says, he went, Baskaran, we are here. That question is up there. So it's one of the key questions in emergence. How inanimate things can join together and consciousness can emerge. before we understand what is consciousness, firstly we have to define what it is. So lots of debates about it, and there are people who cheat.
Yes.
That's a very important thing for young people to be aware of, because science is experimental. If you understand it, I should be able to understand it. When it comes to consciousness questions, people speculate enormously, so they go astray. Whereas other quantum biology that I was talking about, like photosynthesis, they are very hard experimental facts. So you can understand, do the experiment, repeat it. So there is a beautiful work by Francis Crick, the famous Watson and Crick. He says, yes, consciousness is a very important question. We roughly know what it is, but you and me, let's agree that there is something like a consciousness. Let's make a hypothesis about consciousness and test it. He says, because we have these machines, fMRI, functional magnetic resonance, it shows a particular way of brain firing pattern when you are in a happy state. When you are in an unhappy state, firing pattern changes. When you are grammatically correct, so there is a correlation between conscious states, and so he says that's the way we have to approach the problem, rather than speculating that quantum physics plays an important role.
Yes.
Quantum mechanics is already mysterious, so it's possible it's working, but we do not know. So one has to be humble, and so if somebody says that he can explain using consciousness, using quantum mechanics, please be careful with him.
Yes. Okay, sir. Yeah. Thank you for clarifying that.
Yeah. Oh, qubits, for example. So, sorry, I didn't have time. There are many qubits. For example, nuclear spin qubits, superconducting squid qubits.
It's practically possible, no? It's going to come in.
Yes, in fact,
it's there.
For example, if you go to IITMadras, there are already some superconducting qubits available. Similarly, NV center qubits, they are there. The main problem is decoherence. These qubits, they are isolated from the rest of the world, they will work wonders.
The Chinese are already using it, qubits.
Correct. So, then, there are, Chinese are using it, some of the qubits like optical, there's something called boson sampling method. So, they have some kind of qubits. So, they are far ahead in many directions, but not completely. Whenever there is a news hype, you should be careful.
That superconductivity at room temperature is possible, huh? Superconductivity.
So, it's a new question that you are asking. I am of the opinion it's possible. In fact, that's a separate lecture I'm very happy to give. Possibility of room temperature superconductivity.
No, your slide only shows that superconductivity at room
it's possible, in my opinion. We can discuss it separately. But it's like I call it as elusive superconductor, because sometimes they appear, sometimes they don't see. So that means things at nanoscale are changing very fast. So we are not able to reproduce. So science becomes agreeable when there is reproducibility. So we have to work towards reproducibility rather than saying that somebody is cheating. For example, there's a beautiful work from Indian of Science, Bangalore, 4 years ago, seeing room temperature superconductivity once in 20 samples. So one is to ignore them, or another is to take seriously. I have taken them seriously, and according to theory, it's possible. But something else is going on. I'm trying to understand what's going on. So from theory point of view, it's not impossible. Room temperature superconductivity is not impossible. That will change the world now, if that happens. Another revolutionary development.
Audience, we can have 2 more questions.
Hello, sir. Yeah. Actually, I wanted to connect my question with him, but anyway, the question is in the quantum physics, the interpretation of reality. Actually, I'm a Buddhist monk myself, so I have done lots of meditation. And I have got different states, mental states and other things. And Buddha himself, he talks about reality. Reality means this universe. So I would explain in two phases. So one is he says that the same thing he says, unless a conscious observer observes, then there is no universe. If they don't observe, you can say that there's no meaning to it.
So let me interject.
Yeah.
See, I am studying stones and pieces of magnets and liquid and so on. So things like consciousness are far beyond the present condition. So there are analogies, like he says, Maya, or various states. There are analogies. But however, I don't deny that meditation can be of help, no question about it. Mental state can be, you can, brain plasticity and various things are there. So you can control your health of the body by meditation. I do believe that, but that is nothing to do with consciousness, question that you are asking. So I am not able to answer that question of consciousness because I am limited to simple quantum mechanics, which I don't understand. So things like consciousness is too high for me. For if any physicist tells you that he understands consciousness, be careful about it. Because Swamijis can say that, they can afford to say, because they don't know quantum mechanics. They can see similarities. A famous, I don't want to name in the public, somebody says he understands consciousness. But when people questioned him, physicists, regular serious physicists, wanted to understand what he says, he was talking something very different. So some similarities should not be misused. Yeah. No. See, like at personal life, calming one's mind is the most important thing, right? Meditation is very important. I totally agree with that. So similarly, people should not confuse religion and the belief in God with science. Science is very different. It's just addressing materials issue. Very simple thing, rocks and stones. And whereas, because any scientist who says that he understands everything based on atoms, don't believe him also. So you understand to some extent. Thank you. Yeah.
Now the final question.
Sorry?
It all started with planks, if you...
Yeah.
As you said. So, like, what made his guesswork? What are your guesses on his guesswork? Like, how he made this guesswork? Like, he made up to 10 to the power minus 27, as you say. Like, what are the... how he is able to shut up and do this?
See, this is a very deep question about our own intuition. How there are situations wherein we make some guesses, and in this case, quantitatively he made this guess. But he was following no magic, just precise mathematics. He said there is a curve like this. I'll fit it to an exponential, the Bose-Einstein, in the Planck distribution form. Then he needs to introduce a quanta. And he tried to explain it using this idea of energy quanta. That's all. But it was a curve fitting, nothing more than that. In fact, as Abraham Pais in one of the articles says, it's like a madman's curve fitting, but there was something divine about it.
Okay. What is the relation in the fittings?
Sorry?
What he is able to, how he related might be, the equation says that, fine.
Yeah. So you are, like, when you have a formula curve going like this, you say it's best fit quadratic. Correct? Okay. Similarly, something like the tan hyperbolic. Here is a different form. So you made that guess, and then that naturally involved a constant which is Planck's constant. And then he tried to explain that using the idea of energy discrete. So just educated guess, as they say. I don't know why Planck himself thought about it. I don't know. I'm not a psychologist. I don't know how the way mind works. Our mind is a very mysterious thing. You will agree. Mind is the most mysterious thing. But scientists will say never mind about it. You do your work. Yeah.
So with this, we come to the end of the question answer session, and now it is time for felicitation. May I call upon Dr. S. Santana Karthikeyan, Librarian and Information Officer of Anna Centenary Library, to present a memento to our chief guest, Professor Baskaran. Now may I call upon the questioners to come on. Okay. All the questioners, please come here. You will be given a token of appreciation for asking questions in this session. Thank you, everyone. And now it's time for vote of thanks. I call upon Ms. Sridevi Baskar, Librarian and Information Officer of Anna Centenary Library, to deliver the vote of thanks for the Silver Jubilee of TNtalk.
It is my great pleasure to deliver vote of thanks on this special occasion celebrating the Silver Jubilee of Tamil Nadu Talk. First of all, we thank our esteemed speaker, Dr. G. Baskaran, IIT of Madras, for his brilliant innovation talk on the topic how quantum physics has impacted society in the last 1 century, and thanking him for his insightful speech with all. As a visionary thinker, he globally renowned for his pioneering contributions to condensed matter physics and influential discoveries. It is a moment of great privilege and joy to express our thanks on this Silver Jubilee occasion of TNtalk to Dr. G. Baskaran, a towering personality in theoretical physics and a guiding force in scientific discovery. Thank you, sir. And Anna Central Library, magnificent tribute to knowledge and culture, renowned famous for architectural marvel, one of the largest libraries in Asia, along with Innovation, conducted TNtalks, many TNtalks, which has initiated by Government of Tamil Nadu and completed 25 programs in this series, and showed unveiling, insightful, fueling inspiration by famous popular leading personalities, disseminated their knowledge through presentations and educate the users of this library, and also research scholars and students, and benefited by many various people of this library in various domains such as science, technology, social sciences, humanities and governance. We also convey our special thanks to our director, Directorate of Public Libraries, Joint Director, and Chief Librarian Information of our Anna Central Library for executing such kind of programs. We also convey our special thanks to our technicians, Kalvi Channel, IT team, and also to housekeeping staff, and librarians for their tireless work and their contributions and their full support to make these programs a grand success. We also share our special gratitude to our users for participating in the question and answer sessions and sharing their thoughts and experiences and knowledge. It is such coordination from all for making this program a grand success, and thanking all for their presence and constant engagement and support, and this making all TNtalks a memorable one. Thus, we are expecting strong support from all and all users of this library for forthcoming programs also. Thank you all.
Thank you, ma'am. Finally, it is time for National Anthem. Let us all raise for National Anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जाहे तव शुभ आशीष माघे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Thank you all.